The last little bit of the equilibrium section is on acids and bases, because many acid-base systems are equilibrium systems. And so we can understand acid bases through the lens of equilibrium, and we can understand equilibrium through the lens of acids and bases. So it's powerful in both ways. So there are three little bits we're going to talk about here. The first is Bronsted-Lowry definition of acids and bases. And the two theories that lead up to this are, first of all, the the Arrhenius definition of acids and bases, where acids are things which ionize to produce hydrogen ions in solution. Bases are substances that dissociate to produce hydroxide. This has a couple of limitations. Limitation number one, it does not explain bases which don't contain hydroxide. For example, ammonia is a base. It doesn't contain hydroxide. Arrhenius doesn't explain that. So the theory can be improved. Also, that hydrogen ion is so small that it has a charge of 1+, that it's not going to like to exist on its own. It's going to actually latch onto something and form hydronium, H3O+. So we need the modified Arrhenius definition of acids and bases, which says that acids are things that react in water to form hydronium. So acids react with water to form hydronium ions, H3O+, and bases react with water to form hydroxide. That nicely explains how weak bases can exist. However, there's still limitations. It assumes that all acid-base reactions take place in water, when in fact they don't all take place in water. You can have an acid-base reaction taking place in another solvent. So in order to solve that final problem, we need another definition. We need the Bronsted-Lowry definition of acids and bases. And the Bronsted-Lowry definition of acids and bases, it really fits into modified Arrhenius, at least the way that I like to explain it in class, where if you have something that's reacting with water to form hydronium, let's say you have hydrochloric acid. It's reacting with water to form hydronium. Well, the way that it forms hydronium, you need to give the water an extra hydrogen, so it means that one of these hydrogen ions is transferred to the water. And that's what Bronsted-Lowry says. The Bronsted-Lowry definition says that acids are substances which donate a hydrogen ion or a proton, which we could call it, because a hydrogen ion is just a single proton. It doesn't have any neutrons. It doesn't have any electrons. And a base is something which accepts a hydrogen ion or a proton. So really, we're tracking hydrogens now. So let's look at how that works. So for hydrochloric acid, if we want to show how it can be an acid using Bronsted-Lowry definition, we say, okay, it means that this thing is going to be a hydrogen ion donor. So it's going to give an H+ to the water. When it does that, the water is going to turn into hydronium because it's picked up an extra hydrogen ion. And the thing that's left behind is this chloride that's got a negative charge. So this would show HCl acting as an acid. Now what about ammonia? We know that ammonia has basic properties. So how does it act as a base? Well, it has to form hydroxide, and it does that by stealing a hydrogen ion from the water. When it steals a hydrogen ion from the water, that forms hydroxide, and the ammonia now becomes ammonium. And now here would be an example where a proton is being transferred from an acid to a base. So we have the hydrogen carbonate ion here and the hydrogen sulfate ion. Now if we look at my products, the hydrogen carbonate has lost its hydrogen ion. So it must have been acting as the acid, transferring the hydrogen ion to the hydrogen sulfate ion because it becomes sulfuric acid. And so when it does so, that means that this guy was the acid and this guy was the base. Now you notice that the hydrogen carbonate turned into the carbonic acid. So these guys are really a pair, and they're what we call a conjugate acid-base pair. This base, when it gained a hydrogen, it turned into sulfuric acid. That means that this is my second conjugate acid-base pair. And this is a reversible reaction. Note the equilibrium arrow here. So if the reaction was going the opposite direction, if it was going this way, well then, which of these would be acting as the acid? Which would be acting as the base? Well then, the sulfuric acid would have transferred its hydrogen to the carbonate, right? To form hydrogen carbonate. So the hydrogen would be transferred like this. So that means that the sulfuric acid would have been acting as an acid, and the carbonate would have been acting as a base. And so notice that from this first conjugate acid-base pair, the acid turned into a base. And for the second pair, this base turned into an acid. And that will always be true. You will always have conjugate acid-base pairs in a reaction like this. The acid always turns into a base, the base always turns into an acid. So we could go back and label my top two the same way. The HCl here, it donated a hydrogen to the water. So the HCl was acting as an acid, water was acting as a base. Now, the water turned into hydronium, so this is a conjugate acid-base pair. That means that the water turns into an acid. The hydronium could act as an acid, donating a proton if this reaction was going backwards. The second pair is the HCl and the Cl-. The acid here turns into a base on this side. And if we want to label my last one, now the water was acting as an acid because it donated a proton over to the ammonia. The water turns into its conjugate base, hydroxide, and ammonia turned into its conjugate acid, ammonium. We always have conjugate acid-base pairs. This also highlights that water can act as a base and it can act as an acid because it's an amphiprotic species. Here are a few more examples here. We have ammonia and the hydrogen sulfate ion. Now the ammonia would act as a base. The hydrogen sulfate ion would act as an acid. So which way is the proton going to go? It's always transferred from the acid to the base. So that means my products are going to be ammonium because this guy's gained a hydrogen. This guy's lost one, so it'll have turned into sulfate. For the phosphate and hydrogen carbonate here, notice that the phosphate doesn't have any hydrogens, so it can't act as an acid, has to be a base. That means that the hydrogen carbonate is the acid. Again, the proton's transferred from the acid to the base. So the phosphate will gain an H+, so it will be HPO4. It only has a 2- charge now because it's gained a positive thing. This guy's lost a positive thing, so he'll be CO3 2-. And then finally, here's acetic acid reacting with sulfate. Remember, it's this hydrogen on the end that would be donated. So the acetic acid will act as an acid. Sulfate will act as a base. It doesn't have any hydrogens to give away. So the proton will be transferred like this. That means that the acetic acid will turn into acetate. And the sulfuric acid, or the sulfate rather, will turn into hydrogen sulfate. And we could ask you to identify conjugate acid-base pairs. So here's a conjugate acid-base pair here. Here's the other one, right? You look for what did I turn into? The phosphate here turned into hydrogen phosphate. The hydrogen carbonate turned into carbonate. The acetic acid turned into acetate. And the sulfate turned into hydrogen sulfate.